and see if it works. Okay, we'll see if it records.
Sure.
Okay. I'm posting a link into the chat box. It's slide. If any of you want to, like go back, a couple pages or something, you can just download a copy of my slides. I've got a dual screen set up so I can see the chat box and the participant list. If you got a question, you can certainly type it into the box, or there's like a raise hand function in Zoom, and it like flags you on the participant list. If you you can use those features if you want. I should see what you got there. Let me move this over to here. Bruce says it doesn't improve the audio quality much, but it makes me look like Larry King. So, all right. So, all right. Resolution of singularities is my topic this afternoon. It's a topic in algebraic geometry. What do we got? There we go. A little sluggish. I wonder why that is. Okay, so just to set the stage, what is algebraic geometry? What are we talking about? Hold on a second. Let me take a look at this. Okay, looks reasonable. Okay, so yeah, prototypical problems in algebraic geometry. Most algebraic geometry textbooks, you see this. Where's my pen? Oh, there it is. Okay, you see systems of polynomial equations. We're looking for solution sets, x, y, and z that solve, these equations. There's a kind of another route into algebraic geometry that I like, and that is to look at it from the standpoint of abelian integrals. So we have, we're trying to integrate something involving a square root, in this case 1 over square root of x to the 4th plus 1 dx, and what we want to do is replace the root with a y, and we just say y squared equals x to the 4th plus 1, and now we're trying to integrate 1 over y. And what I like about...
What's the abelian mean?
What's that?
Brent, what does he consider the word abelian?
Well, I mean, it's named after Abel, the famous, is he Norwegian, was he, I think? Was Abel Norwegian?
Okay, some integrals that he looked at.
Absolutely. It's
Yes.
integrals where you have polynomials and roots of polynomials. That's just by definition now an abelian integral. So, what I like about it is, first of all, it involves solving a differential equation, which is more in line with what I'm trying to do than looking at systems of polynomial equations. And right off the bat, we see this business of a function on an algebraic curve. We're not just interested in the values of x and y that solve this polynomial equation, but we actually want functions on the curve, or even differentials, 1 over y dx. And typically when you have the textbooks that start with systems of polynomial equations, you get into functions, but a little bit later on. I kind of like to think of functions as like first-class objects, that we're very interested in studying functions. And we're going to restrict our attention to, of course, polynomial equations and then rational functions. When I say a function, I'm almost always talking about a ratio of polynomials, just because by limiting ourselves to polynomials and rational functions, we just have a huge battery of tools that we can bring to our disposal, and that's really just kind of the program of algebraic geometry. So,
your example is not rational.
Which one? This one here?
Number 2, abelian integral.
Yeah, well, yeah. It is. From a, I'm saying
it's algebraic.
What's that?
It's algebraic.
It's algebraic, yes. Algebraic geometers usually bandy around the term rational function as rational in all of our variables. So if we got an x, y, and z with a polynomial relationship, any rational function in both x, y, and z, y becomes one of the things we can have a rational function in. So it doesn't have to be a rational function. An algebraic function would probably be the best term. But yeah, I use the word rational function, or just function. We're just about functions. When I talk about just a function, I always mean an algebraic function, ratio of polynomials of these variables related by polynomial equations. So this is like one of my prototype problems that I'll come back to this a lot today. Y squared equals x cubed plus x squared, and there's a plot of it in the real plane. And we see right off the bat we have a singularity where the curve self-intersects at this point S. Right off the bat we see that we don't have like a clearly defined tangent line. We got like two tangent lines, so how do we do derivatives? How do we do series expansions? Obviously a lot of our standard tools need to be patched up a bit in order to deal with singularities. The good news is that that's pretty much as bad as it gets. We've got techniques for dealing with singularities and algebraic curves, and once we manage to deal with them, then we're kind of home free, and that's it. That's all we need. That's as worse as the curve gets. And these algebraic singularities, and we do know rough. Yeah, we do know. We got a lot of good techniques for dealing with them. Here we go. Now, something you might think is that a function, a rational function, an algebraic function, defined on one of these curves would at least have to have the same value at the singularity in both of its branches, and that is not true because our algebraic function field has lots of what do they call them? Shoot, I can't think of it. 0 over 0, indeterminate. You got a lot of indeterminate values in our. Here I am. A lot of indeterminate values, like y, like the singularity here is at 0, 0. It's at the origin. So y over x, 0 over 0, and absolutely the way to look at this is to treat it as a removable singularity and look at its limiting value. So along the a branch of the curve, its value is 1. That's the limiting value of y over x there. On the b branch, it's negative 1. If I subtract 1 from it and I get y minus x over x, then the values are 0 and negative 2. I can take the multiplicative inverse, x over y minus x. I can even have a pole on one branch of the curve and a finite value at another branch of the curve. Both of the singularity. It really depends on which of these two branches you're on. So they really do tend to act like completely separate points, even though there's only one point on the plane. So Wikipedia's page on resolution of singularities defines it as asking whether every algebraic variety has a resolution, a non-singular variety with proper birational map. Proved for characteristic 0, open problem in characteristic P. I'm not sure. I mean, it's a definition of terms. Is resolution of singularities just asking whether it exists? Is it just an existence proof, or do you actually want to do something with it? I'm going to talk about how we do things with singularities. So maybe my definition of resolution of singularities is a little broader than just this existence proof. Curves. Restricting our attention to curves rather than arbitrary varieties. Every algebraic curve has a unique non-singular projective model. Kolar, 2007, lists about 20 ways of proving resolution of singularities of curves. Kolar is a good book. I've only read the first chapter. That's his historical survey. Yeah, there's about 20 ways of doing this. I'm going to look at like 5 of them today. Riemann's method, Newton's method, Puiseux series, blowing up, and normalization. I don't know the other 15, and I couldn't jam them all into one lecture, even if I could, even if I did know them. So let's start with Riemann. a plane algebraic curve. So we're in an x, not doing space curves. I've got a space curve later in the lecture, but plane algebraic curves, so just in the xy plane. Definitely looking at over the complex field. And we can treat it as a polynomial in y with coefficients that are rational functions in x. And I mean, this example here is the one that we're looking at, y squared minus x cubed plus x squared. So our y squared coefficient would be 1, our y coefficient would be 0, and our y to the 0th coefficient is going to be negative x cubed minus plus x squared. And then we can fix any value of x. That'll just fix these values. These a values become fixed. We get a polynomial on y. The complex field is algebraically closed, so we can just extract its roots, or at least at most n roots. When can we not have n roots? Two basic cases. First of all, this leading coefficient, this a to the n term, this could be 0. This thing could become 0, and then we'd get a polynomial of degree less than n at those points. That's the case where at least one of these sheets, because as you move x around, the n roots in y trace out sheets, in the complex plane. It's a little hard to visualize it. It's very best, I tend to visualize it like the x plane, and then I treat it y as like one-dimensional, so it becomes like a three-dimensional picture. As you move around in the x-plane, you're tracing out sheets in the z space, the vertical space there. So if that leading polynomial is 0, then you have a sheet that diverges away to infinity. You have basically some kind of a pole there. I'm not too concerned about that case. I can just kind of look at it from the standpoint of projective space and just change to a coordinate system where that point becomes finite. It's probably like my favorite way of dealing with points at infinity, is just use a different coordinate chart in projective space. Case number 2 is the one I'm more interested in. Root could have multiplicity more than 1. This is the case where 2 or more sheets touch. So we got these 2 sheets and they come together, and there's a point of intersection. That could be a singularity. It doesn't have to be a singularity, but that is the case where we have 2 sheets, they come together, they have a single value, and we want to analyze that a little bit more. So we can isolate these points fairly easily. Case 1 points, we just solve, a to the n x equals 0. I'm treating just solving a univariate polynomial over the complex field as just kind of like a primitive operation. We can just extract roots. And then the case 2 points, we want to look at the GCD of the defining polynomial of the curve and its y derivative, its partial derivative with respect to y. And the reason is because if you've got a multiple root, if you got some if this as a function of x, if it's the x root has multiplicity more than 1, then the derivative, the same root will appear in the derivative, and you get you get shared roots between your function and its partial derivative. So you can either use the GCD or more simply the resultant, and that gives you a polynomial that you solve that and you find all of your case 2 points here. So just by extracting roots from polynomials, doing nothing more complicated than a resultant, we can find the locations of all these problematic points. Everywhere else, the complex implicit function theorem tells us that it is analytic. This is from Hormander, Introduction to Complex Analysis and Several Variables. I think when we do calculus, we usually have like our standard calculus class, which is in real space, and then we do like a multivariate calculus class, which is an n-dimensional real space, and then of course we have a complex analysis class. Now we do all of it again in complex space, and in principle we should have a I don't know. I never took a class in multivariate complex analysis, but it logically should be there. I guess people just get calculus fatigue or something. Anyway, this is definitely the complex multivariate implicit function theorem. It's just different. It's a different theorem than the one you get in a standard multivariate class. C's instead of R's. The statement of the function is identical. W and Z, we got J, M and N here are 1 in our case. Just one W, one Z. We want Y as a function of X. So W is a function of Z, and the partial is with respect to W, Y in our case. And since J, K, M is 1, so this determinant is just a single partial derivative. And when this partial derivative is non-zero, the implicit function theorem tells us we got an analytic function. I'm thinking like y as a function of x. And if y is analytic as a function of x, then all of the polynomials and y and x are going to be analytic, and rational functions, algebraic functions in these two variables are going to be at worst meromorphic. What happens at a multiple point? What happens when that partial derivative is 0? This is a diagram from Bliss. And I mean, what happens? First of all, the multiple points are all isolated, which is to say there's only a finite number of them, so you can always find like a disk in the complex plane around the multiple point, and where it's completely analytic in the region around the disk. So what happens is you start someplace, I guess B tick, okay, and you go around B tick, or I guess how do we do this? We'll start here. We'll start at B double tick. You go all the way around the thing, and you come back, and what happens? You're either back to where you started from, or you've moved to a different sheet, and then you go all the way around again, and after a finite number of these revolutions, you get back to where you started, and that whole progression there, we call it a cycle. So this is a single cycle. We got to like 7 sheets here. We count them up, and 4 cycles. So we got 1 cycle here of ramification 3. Ramification is the number of times you go around. This one here, you went around and came right back to the same place you started from. So it's ramification 1. This is a cycle of ramification 2, and a cycle here of ramification 1. And that covers all, when you have all these multiple points, you can have multiple cycles, they can have different ramification indices, but that really is kind of as bad as it gets. If we can handle multiple cycles and cycles of non-trivial ramification, we're kind of done. So what happens at a single cycle? If we've got, in this case, ramification. Yeah, question?
Brent,
No?
can I ask a question? So as you approach this point of singularity, what you're saying is the direction of approach will cause, in one case, you'll have to run round it 3 times, and another time you'll have to run round it -1.
1.
In a sense,
That's just a
yes.
dash.
Oh, that's right. Thanks. 1
I mean,
or 2 or 1.
remember that there are, in this case, 7 roots. We're dealing with like a 7th degree polynomial here. So there's 7 roots. So I say approaching it not so much from the direction in the x-plane, but it's a question of which of the sheets in the y coordinate, in the y-plane you're approaching on. You can approach kind of in the x direction however you want, but you got 7 possible, this is some 7th degree polynomial on y, so you got 7 possible values of y, and you pick one, and you kind of approach the singularity, but don't have to go right up to it. You just loop around it. You loop around it, and you see when you come back around, are you at the same value of y, or you're at a different value of y? That's the question. Okay?
Okay.
All right.
Okay.
So you move to a different sheet. In other words, you have to go through all 3 sheets to get back to the origin
That's right.
where you started.
And there's only a finite number of sheets, so you eventually get back to where you start.
Mm-hmm.
So if we have one cycle, in this case a cycle of ramification 3, we had to go around 3 times to get back to where we started from. Actually, the individual cycles are analytic. In this case, I have a t-plane, just an auxiliary variable t, and I define x as whatever my x coordinate is plus t cubed. So as I go in a circle around the t-plane, in the x-plane, I cycle around 3 times. And then I can just plot my y values on my t-plane. I can assign these 3 sheets to these 3 sectors, however I want. And I get, y, I'm plotting y as a function of t. It kind of like unraveled the sheet and made it flat. And so I got my x's that map to t cubed plus whatever the origin value here is, and then the y values. And the implicit function theorem is telling us that the thing is analytic everywhere else. The question is it also analytic at the center? And Riemann's answer was yes. His theory on removable singularities, we have an open subset of the complex plane, a point of D. The function is holomorphic everywhere except at the point A. And that's the case we got here. And the question is, can we take this, it's completely surrounded in the t-plane by like a domain of analyticity, a holomorphic region. And the question is, can we holomorphically extend the function to the origin? And the answer is yes. And probably the easiest way to see, all 4 of these conditions are equivalent. Probably the easiest way is 3. There exists a neighborhood of A on which f is bounded. Remember, this whole thing is like this whole thing is cycling around, so we can just kind of put this whole thing in a cylinder in both the x and y planes. You can surround it with like a cylinder that encompasses the whole thing, and you see all the y values are bounded here. So we get bounded, we get the whole thing bounded in this neighborhood of A. That gives us condition 3, and Riemann proved, and actually the proof is on the Wikipedia page as well, that means we can holomorphically extend to A, and we got the thing holomorphic everywhere. So that means that each individual cycle can be fairly easily converted into an analytic. It's analytic on the individual cycles. If there is a single cycle at the point, then we just got a local analytic coordinate system, and we're kind of done. Otherwise, we need multiple t-planes. So this is the singular case. We have multiple cycles, and they meet at a point, and like this is kind of like what it looks like from a standard. Think of it as like a manifold. Is it locally Euclidean? It's like almost locally Euclidean. It's like 2 planes that touch at a single point. So it's the union is collectively. You can take all these different t-planes. They're collectively 1-to-1 except at the singularity where they're many to 1. Each t-plane is going to have, you can have more than 1 points, one for each of these cycles, and they're all going to map to the same point at the singularity. And everywhere else on the algebraic curve, it's the implicit function theorem is telling us that it's analytic. So this is like the worst it gets in terms of it's like almost a manifold. And if you patch it up with these, you need a couple extra points at these singularities, and it then actually becomes a manifold. And that is basically like a proof sketch of Riemann's theorem. This is from the Kolar book. This is his statement of Riemann's theorem. F is a irreducible polynomial. It defines the curve C. There is a one-dimensional complex manifold C bar and a holomorphic map. C bar into C. That's the C bar is like the union of all these different charts. Think of it like topology. It's and it's biholomorphic. You can map from C back to C bar except at finitely many points. And the finitely many points are the singularities. You can't quite map back there because it's a one-to-many map. Okay, and that's basically Riemann's construction that I always tend to keep in mind when I'm working with these things. Very geometrical, just good for me for like visualizing how these algebraic curves work. All right, so moving along. Newton. Newton is actually, we're kind of moving backwards historically. Newton is the one that has the first. I took it. It's 1676, I believe. A letter in 1676. Newton described what is now called a Newton polygon. Basically, the issue is here. Okay, so if we, not thinking about it historically, but thinking of it structurally, Riemann told us that, with a slight modification to these singularities, we got a structure that is analytic everywhere. Okay, so it's analytic everywhere. The next thing you would want to do is let's figure out some series expansions. You think we're going to plug in some series expansions, and what do? We just plug. We set up some series expansions and plug them into whatever our defining polynomial is. The problem is this number here, the ramification index. We don't know what this is. We could, I guess, try to set it up as just t to the r, and we got this extra r power floating around in the thing. I don't know. I don't know. Could it be done? I'm not sure, but it's not necessary because Newton showed us how to find the power, how to find the ramification index of one of these cycles, and that's the Newton polygon construction. What we want to do with the polynomial, let's just think about it as the singularities at the origin. We change variables if it's not. We're going to mark the point ij with a big dot if the monomial, we got these it's the powers. It's the I, the j. We don't care about the a. All we care about is that it's not 0. We're going to mark the point ij. It's the power. So they're all integers. These are all integer points. And then we want the lower convex hull of this polygon. Let me just show you an example. So here is our sample curve. Y squared equals x cubed plus x squared. We're going to plot the x coordinates on the y. Point x is on the y-axis, x is on the y-axis, or vertical axis, y is on the horizontal axis, and we're plotting the powers. So for this monomial here, it's 2, 0. For this one, it's 0, 3. For this one, it's 0, 2. That's our polygon. These 3 points, we're interested in the lower convex hull, which is just this red line here. We see that its slope is -1. That tells us what the ramification is. The denominator gives us the ramification. It's 1. And then the width, how many steps we had to move in the x-axis to cover the thing, that tells us how many cycles we needed. So this tells us that for this point S, we have 2 cycles, and they have ramification 1. So we're going to have 2 cycles meeting here, and the ramification index of both of them is 1. Another example. Let's do this point here. This is actually another kind of troublesome point on this curve. The implicit function theorem just straight up doesn't, I say straight up, just the simplest application doesn't work. The derivative here with respect to y, the partial respect to y, goes to 0 because the tangent line becomes vertical. We don't have you can just see as a function of x, we do not have a well-defined. It's not a singularity, but because of the vertical tangent, we can't just do a simple series expansion at x. So we change our variables. We want to just shift basically the point to the origin, or just use x plus 1 instead of x. And this is with the polynomial, it's the same polynomial, just using x plus 1 instead of x for our monomials. And this becomes the Newton polygon. You see, now we've got this x plus 1 term that gives us this 0, 1. This red line now is our lower convex hull. Its slope is -1/2. That means you have ramification 2. So this is double ramification covers like 2 entire cycles or 2 entire loops around the plane. So that's 1 cycle, ramification 2. Just divide 2 by 2. You get one. It's 1 cycle with double ramification, and it is not a singularity. It is a single cycle with ramification 2. And then you think to yourself, well, how does this work? This is my explanation of how Newton polygons work. I think the best way to look at them, to understand them, is to think about it in terms of valuation. So valuation in algebra, we have a field K. Our field is the fractional power series in one variable, x. So just power series in x. They're actually going to be fractional power series in x. We want a group Q. Our group is Q. Our gamma in the definition. Our group is Q. It's just rational numbers. And then our valuation is the lowest power that appears in the series, and it does satisfy all these properties. Its valuation is infinite if the function is 0. Multiplication of the function causes addition of the valuations, and then the valuation of a sum is greater than or equal to the minimum of the 2 valuations with equality if the valuations are not equal. If they're equal, then you might have inequality here. You might have a greater than equality if they're not equal. Let me illustrate. Okay, so the valuation of x plus x squared plus x cubed is 1. Just looking at it, there's like a power series. The exponent, this lower numbered exponent is 1. Okay, here's a power series, x to the 1/2 plus x to the 3/2 plus x to the 5/2 plus a bunch of other stuff. Its valuation is 1/2. Again, the lowest power in the power series, 1/2. F x squared plus x, g x squared. Valuation of x, 1, because the lowest power here is 1. Valuation of g, 2, because the power here is 2. The valuation of their product, which is x to the 4th plus x to the 3rd, is 3, which is the sum of 1 and 2. Okay? That's basically how valuations work in our framework here. So now I want to take our polynomial. I want to think about it in the terms of like algebraic extension. I mean, the curve is irreducible, the polynomial is irreducible, but if I extend into the field of fractional power series, actually, I can treat this like just a formal extension into an algebraic extension to get factorization, but actually what I need is just the field of fractional power series, and the polynomial actually does factor completely if I allow fractional power series in x and then polynomials in y. So here is my polynomial in y. Its coefficients are rational functions, or probably rational functions in x. And then I can factor it, and these gammas are fractional power series in x. And then the question is, what are their valuations? So if I multiply it all back together again, I'm just assuming that it's monic here. It just simplifies the presentation. If I multiply everything back together again, let's look at the lowest, the constant, the 0 term here. It's all of the roots multiplied together. That's going to be my a0 term. And since they're all multiplied together, what that does to a valuation is we sum the valuations, and that is the valuation of the a0. Well, let's see. That is exactly the lowest point on the Newton polygon over here. The a0 is this vertical line here, the vertical axis, What is the valuation here of this A0 term? It's 2. That is the lowest point on of these 2 points. This is the lowest point. The height of this is going to be the sum of the valuations. That's what this height is going to be. Both the valuations are 1 because we have a singularity with 2 cycles, and we add them up and we get 2. That's where this 2 comes from. Here on this one, the height here is 1. Why? Because we have a cycle with ramification 2, so this is a fractional power. Our power series is going to look something like this. We're going to have this t. Actually, this would be x, but we're going to have fractional. X is going to be something like t squared, and then we're going to do a power expansion in t. It's analytic in that t plane, so it's going to be something like y is going to be something t plus t squared plus t cubed. But as a power of x, it's going to be like x to the 1/2 plus x to the 3/2, blah, blah, blah. As a function of x, it's going to be a fractional power series. Our power is going to be 1/2. That's the inverse of the ramification index. That's how we got the 1 here. 2 sheets, ramification 2, 1/2 plus 1/2 is 1. So that is the height on the left-hand side of the Newton polygon is just the sum of all the valuations of all of our roots. And then if we start like moving to the right along this polygon, what happens if we step now 1 to the right? Well, now we have a sum of products of the roots, but now with n-1 roots. You have n-1 terms and n-1 roots, and that's going to be, the minimum. The valuation of a sum is the minimum of the valuations of the individual terms, and each one is going to be a sum of valuations minus 1. One of the valuations is going to drop off each of these, and we're either going to get the minimum of all these valuations, or there could be cancellation. If you have like a series like x plus x squared, blah, 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 valuation 1, and I add to it negative x minus x squared minus blah, 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 that's also valuation 1. When I add them up, I just get 0. That's valuation infinity. That's the case in the valuation where if you have the same valuation, you could get that inequality. It could be greater than the minimum. And we can actually handle that just by sorting all these valuations in descending order. We start with the largest ones here. Let's say J1, J2 up to Jm are all the same. We just move along the polynomial m steps along the x-axis, and we get to the am term, and that is going to be exact. That is going to be the sum of all the valuations minus m times whatever this largest valuation is, and that is going to cause, that means that in the Newton polygon, in the general case, when you step over and down on the Newton polygon, the difference of the height is going to be the difference in the valuations. The x, the horizontal distance is going to be the number of roots you had to move, and the slope is going to be the negative average value of those valuations. I think the Newton polygon is very simple to construct, more difficult to explain how it works. That's just the best I can do, I think, at the moment. I hope it made some sense. Once we have constructed a Newton polygon, then we know, here's an example. Here's another example of a Newton polygon. Here's a polynomial where it's 3 curves. We can just combine them all together. The Newton polygon construction doesn't require the curves to be irreducible. So let's just take these 3, multiply together. I expand them out, and I get this polygon here. I'm sorry, this polynomial there. And we take all those powers, x cubed, y, 3, 1, 2, 2, 1, 3. We plot them all, And then the lower convex hull is this red line here. So the first segment here, this lowers slope -1. That corresponds to the root right there, where it's going to be y is x, so its evaluation is 1. The horizontal segment here is going to correspond to that solution there. Y is x plus 1, or maybe I should write it 1 plus x, kind of like power series notation. Like its valuation is 0 because of the presence of this constant term. And then, of course, we have the pole, the hyperbola, where it goes to infinity, and that causes, its valuation is -1. Its series expansion, it's exact, actually. It's, I guess, 1 over x. Is that right? Yeah, 1 over x. Y is 1 over x. So its valuation here is -1 because of the 1 over x there, and that's why we get now a +1 slope on the right side of the Newton polygon. So Newton showed that we can construct these polygons and basically just read off our ramification indices. And then once we do that, now we can construct what is today called a Puiseux series. I just take my original polygon. I've done my Newton polygon construction, so I know this ramification index here is, in this case, at the singularity, it's just 1. So I can actually use x as my, I got a t there, but because the r is 1, I can just use t as my x value. X and t are the same thing. I can expand out an x. I postulate a polynomial, beginning of my series expansion here in y, and just expand out y squared, equate like terms with my original polynomial, set things, just set everything together, solve simultaneous equations, and I get 2 solutions here. I can take as many series terms as I want here, and I start to get my power series expansion here. Y is a function of x. This point over here, P, this is the point where I got ramification. Here my R, the Newton polygon showed me that my R is 2, so I actually need to do this. I need to change color to make that a little easier to read, a little clear what I'm talking about here. This 2, so my x expansion is -I plus t squared, so I'm not going to just use x as my t value. I'm going to do my y expansion in t, and then I've got x is equal to -1 plus t squared. I'm going to, or actually I changed here to negative x plus 1 equals t squared, because this thing then becomes t squared to the third, t squared squared, t squared. Substitute all this in. Again, just equate just like terms in t, and it's just solve everything simultaneously, and I start getting the beginnings of my my t expansion here. Y equals t minus 2t cubed plus, and it keeps going. Well, let's see, t cubed up here, I'm seeing t cubed is x plus 1. Actually, I didn't write that right. It's the series are like x plus 1 to the 1/2 minus 2 x plus 1 to the 3/2. So when I put x down here, that is a typo. That should be x plus 1. This is what y's expansion looks like as I start extending it out. Okay, so that is kind of really it's the 19th century version of the theory, but yeah, we can do these polygons. I mean, Newton, heck, that's 17th century. We can do these. Yeah, I mean, Newton was doing series constructions with this in the 17th century, and then of course, with Riemann's construction, made it, put it on like, better foundations. But this is certainly what we could do by the 19th century, is find these ramification indices, construct series expansions. So pretty much any point on an algebraic curve, we can find series expansions. Might be fractional power series expansions. We can do series expansions to find the values in our curve. Okay, so moving along, blowing up. This is something that is completely different. I mean, there's 20 different ways of doing this. Okay, so now I've still got my my y squared equals x to the x cubed plus x squared. Now I want to resolve it differently. I want to think about this thing. Remember, it's like this curve, right? That looks like that, right? And I want to think of it as like a wire. And if I like pull on the two edges of the wire, and I can like stretch it up into three-dimensional space and separate those 2 points. And that's what I'm going to try to do here. I am going to do it. I want a surface whose projection map to the xy plane is 1-to-1 everywhere else everywhere off the origin, and then the z-axis, the origin, I want to parameterize there by the slope. So why? Because this this curve here, again, we look at this curve. I got the slope in this direction here, and I got the slope in this direction here. So if I can parameterize by y over x, I'll be able to separate them in the z-axis, essentially. So I just want y over x to be my z-axis, and so this is my surface. Y equals xz. The idea is that along the z-axis, I'm going to parameterize by this slope y over x, and I've already seen that on the one branch, y over x is going to be 1. On the other branch, y over x is going to be 0. So I expect I'm going to get 2 points, with one with a z-coordinate of 1 and one with a z-coordinate of -1. And that is I just take those two. I take my original curve, take my original equation of my curve, and I take this y over xz, and I now have a three-dimensional variety. It is reducible because it's got the space curve, the stretched out version of the original curve, and the z-axis as well. I mean, if you look at this z, just setting z equal to 0, x equals 0 is y, x equals 0 and y equals 0, and then any value of z will solve this system. So it's a reducible variety. It's the union of the space curve and the z-axis. It can be factored. It's not that hard to do it. Just substitute in z squared. Take this y equals not that one. Take this y equals xz, square it. Y squared equals x squared z squared. We know what y squared is from our first equation. Substitute it in, and we see that we can factor out the x squared. So we got two possibilities: either x equals 0 and y equals 0, that's the z-axis, or we throw away the x equals 0 solution, and we get z squared equals x minus 1, and then our surface, and that is the space curve. That is the the equation of we can substitute it back in and see that it satisfies the original equation everywhere. And then at the origin, when x equals 0 and y equals 0, what happens here? X equals 0, y equals 0, so it solves the second equation here. First equation, x is 0, so z squared equals x plus 1, which is just z squared equals 1. Yeah, z1 or z minus 1, those are the two solutions. So this is a space curve that when you project it down onto the xy plane, it gives us our original curve, but it's actually got it's got like an extra point, if you will. When it loops around, there's actually 2 points lying above the origin, one at z1 and one at z minus 1. And we can even parameterize it. We can even use z as a parameter, and you can't do this all the time. Unfortunately, you cannot always parameterize an algebraic curve, but this one you can. We can just rearrange the equations a little bit and get x and y as as z becomes the parameter. And now we see as we just move along the z-axis, it just traces out x and y, and we have normalized, desingularized our curve by moving up to a space curve. This apparently is like the most popular way of doing it for like higher dimension varieties. I don't know the higher dimensional theory that well at all. I just don't know. I just don't use it. But apparently this works. I mean, you just see the advantages here. We have a coordinate system. I mean, we have like how do we identify these different cycles? Places is the more modern terminology. How do we identify these different places to talk about them? I mean, they each got like a series expansion associated with them. Do we label them with their series expansions? Here we've got, an X, Y, Z coordinate system, so we can see that, we've got actual coordinates that, allow us to separate the 2 points of the singularity apart from each other. We got a system of equations, system of the series expansions are analytic. This is algebra. We don't want, why we got these series expansions floating around. Maybe we don't want them. This is a purely algebraic system here. So there are advantages to this blowing up construction, as it is called. Okay, so my final topic is normalization. I think it's probably a good time to take our coffee break. Does that sound good to everybody? Yes? Andy, you're talking.
Would you provide coffee for everybody?
Oh,
It
well,
depends, Brent, how long is the last part?
I was.
Andy, it's bring your own coffee.
Yes, you got to bring your own coffee. How long is it? I don't know. Maybe another half an hour. Maybe not. Maybe 20 minutes, half an hour, something like that. I'm certainly, the stated time is 6:30. I feel like I'm certainly on pace to be done by 6:30. We can take a 5 or 10 minute break here.
Okay, then we don't have to take break if you.
What's that?
Who's speaking?
Sasha.
Oh. Yeah, so what about continuation of this?
Okay, we can do that. Do you want to continue without a coffee break?
Yeah. This could,
Andy, what's your suggestion?
Yeah, Brent, it depends how long is the second part.
I'm going to say no more than half an hour, 20 minutes, half an hour, something like that.
Well, then let's continue without break if nobody
Okay.
objects.
Very good. Okay.
I agree. Yeah.
Okay.
Thank you.
All right.
You're doing a great job. Nice presentation.
Thank you, Paul. All right. So normalization then. Normalization is kind of the modern way of doing this. I mean, Newton's method is, in a sense, obsolete. I mean, I don't know. It's obsolete the way trigonometric substitution is obsolete. We still teach it. You don't write that into a computer algebra system if you're trying to solve an integral, but we still teach it in our first year calculus classes. But no, like something like Sage, we're doing these calculations. No, we don't do a Newton polygon. What is more the modern style, the modern presentation? Well, it's all done with abstract algebra. It's all rings, ideals, algebras, just the language of modern algebra, modern algebraic geometry, which has, first of all, enormous advantages. It's more general. It lets us work over fields other than the complex field. That is, first of all, like I would say, the main thrust of 20th century algebraic geometry. The whole Riemann construction, if you think about it, is just very closely tied to the complex field. That whole, cycling around thing. How do you do that if you're not in the complex field? If you're trying to do that over Q or some finite field or something where your field includes like rational functions and polynomials, maybe. Not at all clear how to generalize that construction into non fields where your base field is not the complex field or some obvious subset of it, like the algebraic field or the real field. And that's really what the main thrust of 20th century algebraic geometry is, to just figure how to work over arbitrary fields, not just the complex field. And definitely the language we use is the language of abstract algebra. So, for example, our points on our plane. So we have, our complex, plane, x, y, being complex numbers here. and we have a point. We note that the maximal ideal of this coordinate ring, first of all, just the polynomial ring, CXY, the maximal ideals in this in this polynomial ring are in one-to-one correspondence with the points on the plane. And when we work on what's called the coordinate ring, which is CXY modulo whatever the defining polynomial is for our curve, we get the maximal ideals there are in one-to-one correspondence with the points on the curve. So we really can start talking about rings and ideals without losing anything. I mean, losing some simplicity, but we can very easily get back to our coordinate language, and I'll show an example of this towards the end. I mean, you can always get back to our coordinate system because our maximal ideals are just in one-to-one correspondence with our points. So then the question is, how do we do this for places? We've got like a singularity here, so we got this point that's got like two places, two cycles. We would like to find some way of like identifying, splitting apart, those points in that singularity using the language of rings and ideals. And what we found is that for places, the places are in one-to-one correspondence with the maximal ideals of the integral closure of the coordinate ring. That's what we're going for. We want the integral closure, which is called the normalization. And what is the integral closure? It's all elements of the fraction field that are finite at all finite points. Again, just forgetting let's assume that our defining polynomial is monic. We don't have any worry about y to the n is nothing like x up here as a product with y to the n. It just simplifies the presentation. So if that's the case, then all of our polynomials are finite at all of our finite points, because all of our roots are finite. We don't have anything flying off to infinity, no poles. But there are going to be some rational functions, algebraic functions, with non-trivial denominators that are actually finite. Yep. Let's take an example here. Y over x. Yeah, I did that right back to me. Y over x at both of these points, both of these places here, both these places, y over x is either going to be 1 or -1. So actually y over x is integral. It is in our integral closure. So there's things in the integral closure that are not polynomials. In fact, I'll just state this without proof. For this particular curve, this y squared equals x cubed plus x squared, the integral closure is generated by 1 and y over x as a module over the polynomial ring. So basically everything, it's going to be everything in the integral closure here, the normalization of the curve, it's going to be some polynomial in x times or plus some other polynomial in x times y over x. That is the form, and the a's are polynomials in x. That is the form of the integral closure of this curve. And it varies from curve to curve, and a lot of attention has been given to algorithms to compute the integral closure. So, what do we want to do here? We want to see. We have a. Let's just read a little bit of this. Is part of the Wikipedia page on ideals in rings. Extension and contraction of an ideal. And so we have A and B, two rings, a ring homomorphism from A to B, and then we have an ideal in A, and we want to look at its image in B. And we have to, the image might not be an ideal necessarily. We have to consider the ideal generated by all the, take F to be the include blah, 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 blah. The extension is the ideal generated by all the images. All the images themselves may not form an ideal, but we consider all the smallest ideal that contains all the images of an ideal in A, and that's the extension of the ideal into B. And then we also have a contraction. It's just the pre-images then of an ideal in B is the contraction of an ideal in B back to A. So notice here that this statement here, if we have a prime in B, its contraction is prime in A. The converse is not true. And that is the converse being the extension. I mean, a prime in B implies that its contraction is prime in A. That does not mean that a prime in A, its extension is prime in B. And if the remark here, K is a field extension of L, B and A are the rings of integers, B is an integral extension of A, F is the inclusion map, the behavior of a prime ideal under extension is one of the central problems of algebraic number theory. That's exactly the case that we're looking at here. I'm going to, on the next page, I'll unravel all this. But yeah, the prime ideal in A is the prime ideal in the coordinate ring that corresponds to points. When we extend into the algebraic closure, now the ideals correspond to places. And no, the extension is not necessarily prime because one point might correspond to multiple places. So here is the, L in this case, this is the terminology from here. K is a field extension of L, B and A are the rings of integers of K and L. So L is just rational functions in X, just rational functions in X. K is the function field of the curve. It's rational functions in X and Y, modulo the defining polynomial of the curve. The rings of integers, the term is from algebraic number theory. This is now like function fields instead of number fields, but they still use the same terms. The rings of integers for the rational function field, the ring of integers are the polynomials, and for the function field, its ring of integers are it's the integral closure. It's all the things that are finite at every finite point. So for the rational function field in X, it's just polynomials in X, and then for our curve, it's going to be the integral closure of the curve. So we have some prime ideal in A, and this is X. So this is just going to be like points over. And here's our curve, and that's X equals 0 right there. So the corresponding ideal is just X. That's my example X. The extension into B is going to be not a prime ideal, but an intersection of prime ideals. And each one of those prime ideals correspond to one of the places over P, over X. So if we want to figure out what all of the places are at X equals 0, we want to extend into the integral closure and then figure how to execute this decomposition. So how do we do that? Well, let's see here. We're going to look at B modulo the extension of the prime. So how do we do that? Well, let's just look at A and B. Let's just look at set the P, the ideal aside from it. Let's just look at A and B, just polynomials in X and the rational the integral closure here in B. So I've already said that we can write things in B as just some polynomial in X plus some other polynomial in X times Y over X. And then we just start asking ourselves, well, what happens if I did I have another? Did I miss a page here? Yes, this is the page. Yeah, I kind of got these pages mixed up. This is kind of where I'm going here. I'm just considering I got two B's here. I got two of these B's and B's. Each one is a a polynomial in X plus some other polynomial in X times Y over X. Polynomial in X plus polynomial in X times Y over X. This is just the structure of this integral closure. It's a module over the polynomial ring in X. And then I just consider what happens. I'm adding them is very simple. And then what happens when I multiply them? Well, I get A0, the A's, multiply together. I get the cross terms here, like this cross term, and this cross term produces this guy and this guy. And then finally, I get A01 times A11 times y over x times y over x, and that gives me this term here. But if I expand this out, y squared is just x cubed plus x squared. It cancels with the x squared and gives me x plus 1. Of course it does. This is the integral closure. It's a ring. I mean, I can't possibly multiply things together and get something outside of the ring. So yeah, that x squared is going to disappear. If it doesn't disappear, something's wrong. It wouldn't be integrally closed. So yeah, what happens is that when I do this multiplication now, I see that I just this final term, this y squared over x squared term just becomes an x plus 1 term, and I go from I can and once again I've got, this is how I now construct multiplication in B. I got a polynomial in x and another polynomial in x, not quite what I wanted to do there, and another polynomial in x times y over x. So it still has the structure of something in the integral closure. And the most convenient way to write this is using a matrix notation here. Is that I take my b, something in this integral closure, call it b, and I'm going to write it as like a vector of polynomials in A, which is just polynomials in x, right? So I have b as a vector, and it's just multiplying, just vector, but multiplication is by this basis. And then I want to know, how do I multiply my basis elements? How do I multiply by 1? How do I multiply by 1 over x? And this is it. Multiplication by 1 is just the identity right there, and multiplication by 1 over x. This is the calculation I did on the last page, only now I'm just expressing it as a matrix. And once I've got this in matrix form, first of all, I can just reduce modulo the prime now. Let's say P is x. Whoops. Say P is just the x. So I'm going to reduce this thing modulo the ideal x. All the constants just stay constants. The x plus 1 becomes 1, and now I've got I got a finite dimensional algebra over a field, and that's a good. It's an algebra is just a ring. Well, it's a vector space with with a ring structure with multiplication. So I can really treat it as a vector space. And then I just have to add this additional structure of how do I just do ring multiplication. And these matrices are the key to telling me how to do multiplication. So like a vector space plus some extra matrices to tell me how to do multiplication gives me an associative algebra. And in this case, it's an associative algebra over a field. And why is that a good thing? Because we got algorithms to handle this. This is from a 2004 paper. This is the algorithm that is implemented in Sage, decomposing finite dimensional K algebras without using Grosvenor bases. I've seen, you can do it with Grosvenor bases. What we want to do is we have a finite dimensional K algebra. That's what we just constructed. And we want to decompose it. We want to do this is exactly what we want to do. We want to figure how to decompose it into a direct product of these local rings, and then each one of them is going to have an associated prime ideal, and that is going to give us those are going to be the prime ideals in the integral closure that is going to give us the places. And this section 7 in this paper, it's like 3 pages long. I haven't read it. I've skimmed it. I really don't know it because I don't need to. It's just a subroutine. I've just gotten to the point where it's just now a subroutine in Sage. And here's how we do it. We just set up these matrices that define how we do multiplication. We construct finite dimensional algebra right here with these two matrices, and then we call the subroutine that runs the algorithm from that 2004 paper, and it gives us two ideals. And those are the two ideals. E0 is basis element 1. E1 is basis element y is second. These are the two basis elements. E0 is 1, E1 is y over x. So this ideal is 1 minus y over x. This ideal is 1 plus y over x. And we can see that these correspond to the two the two cases, the two places over our singularity. And then notice here I did here x minus 1 reduced it modulo x. We got a 1 here, and that's where I set this up in this matrix. I'm just going to do the same thing with this other point. This is now the point over here. This point over here. So I'm now doing mod x minus 1. That becomes a 0. Put a 0 in here. Do the same deconstruction. Now we just get a single ideal. That's right. We just get a single ideal because we just have a single point, a single place, ramification 2. You can figure that out. If we do it at some other point here, now I think I did it for this example. I did it over here at x equals 1. So this is mod, and I think this is x minus 1. Yeah, the other one was, this is x minus 1. We mod out by x minus 1, and we get 2 here. We get a 2, and now we get two places here. These two ideals. These are these 2 points here and here, and then I can just substitute in and find that like this one here. I set what do I do here? 1 minus square root of 2 y over x. Took the second generator, multiplied it by x, because that is, I can stay in my ring by just, I can stay in my ideal by just multiplying by anything by my ring. So I multiplied this by x. I got this expression here. I know that x is 1 because of this, so I set x equal to 1, and I got this expression here. X just became 1. Obviously, I can just solve for y. Y is the square root of 2. That's this one here. The other ideal is this one down here, where y equals negative square root of 2. So I can recover my coordinates this way too. And this really is the preferred way. It just becomes state of the art. I mean, why? Well, let's see. We have essentially like a coordinate system. These ideals now conveniently label our places. How do I identify a place when I'm working with it? Well, I identify it by just a set of ideal generators. So I can just write out like these ideals here, just like I've got up here on the screen. So I don't need to blow up to get like a coordinate system. I can use the ideal essentially to label the places. I can recover the coordinates here just by playing some games like I'm showing here to get back to my ordinary x and y coordinates. Here is a calculation done with Sage. I start by setting up because everything I just showed, I'm one of the developers that has put a lot of this into Sage. So the latest version of Sage, I think it's like 9.1 or 9.2, but starting with 9.0, we had this in Sage. So I set up a function field over the algebraic field q bar. I set up my here's my the defining polynomial of my curve. Talk about orders, maximal order of OF. This is just that's just the polynomial ring X. I'm going to set up the ideal in there. This is X in A, which was called in a previous slide. It's A in polynomial ring in X. Okay, now this is the maximal order in K, which is the function field on the curve. This is the integral closure. I got a basic right here. I asked for a basis of OK. It's giving me the basis of the integral closure, which I've already exhibited. It's 1 times y over x. And now I ask for the decomposition of ideal I. This is this ideal, and I ask for its decomposition in this OK, in this integral closure, and it exhibits for me the two ideals in the integral closure. I mean, this is how I can take a point and compute what its what the places are, what these places that these singularities are over the point. Got functions to do a series expansion. I just take this decomposition I just did on the last page, pull out the first one out of the list. I can get its residue field, which is the constant field, in this case q bar, along with ring morphisms that go from either the constant field into the valuation ring, which is the local ring there that has everything finite at that place, or I've got a ring morphism that goes from the valuation ring to the algebraic field. The significance of that is that's how I just figure out what my value. How do I know 1 over? I mean, here I'm going to take a residue field of x over y. How do I evaluate x over y? I don't do limits. I simply apply this ring morphism to it, and it tells me that its value is 1. I can use the completion function here to just do this. These are the series expansions that I did half an hour ago. There they are, done up to 20 terms. But no, this is not done with Newton polygons and hypothecating series. This is done with this ring morphism, and you just shift it. You just shift the series left, and you just evaluate the resulting rational function at the place. You just reduce it modulo the ideal, and you just get its value. And as you just shift it by a series of terms, you just get all of its values at these various powers of these ideals, essentially, and that gives you your series expansion. So I mean, you get a Puiseux expansion, but no, internally it's all done with rings and ideals, and I think that's plenty. That just gives you a sense of just how the modern theory works. And it's not, I mean, you see, it's kind of, you read it in these books, Hartshorne and stuff. I mean, there's a computational aspect to it as well. It is more abstract. I'm going backwards now. Like this paper, this Curry-Makdisi paper, notice this works over any k. This is an arbitrary k. We have just a k algebra A. So yeah, it's more general. It just works over arbitrary algebras k, and that's good. I mean, this finite dimensional algebra code in Sage, it works over. I had to set the algebra. Set the base field right there to be the algebraic field QQ bar. So yeah, it's more general. It's more abstract. It works over arbitrary fields, but it's just become the preferred way of doing this. It is, I think, the state of the art. So finally, a couple references. Bliss, that was like the cycling around diagram I had. That was from his 1933 book. That's really where I first started learning this stuff. It's dated, but really it explains the whole Newton-Riemann construction well. Kolar's book that I mentioned, it's cited by the Wikipedia page. It's got a good historical survey. Fulton's book has an entire chapter on blowing up. This thing, normalization of rings, I think this is a 2004 paper. I'm not sure. Maybe not. The other one was 2004. I think, Sage uses singular. How does Sage compute an integral closure, a normalization? It calls singular as a subprogram, and I'm pretty sure here, if you just look in his abstract, the new algorithm of this paper has been implemented in singular for localizations of affine rings. I think this is the algorithm that singular uses. So this is the probably the algorithm that we're using in Sage indirectly through singular to compute these integral closures. And then two final references. Sticknock to GTM and Cohen, which is pretty well known, of course, in computational algebraic number theory. They're both good. Sticknork, though, is really interesting coding theory. So it all tends to be focused on finite fields, and then if you're trying to do something in characteristic 0, a lot of times you're left wondering. He doesn't necessarily give you algorithms that work in characteristic 0. And then Cohen, most interested in number theory, doesn't necessarily give you algorithms that work in function fields. But definitely they're both pretty good reads. And that's it. Thank you. I hope you enjoyed it. And that's my lecture.
Brent, I arrived at 4:47 or so. Can you show your first 2 slides?
Andy, I actually posted a link to my entire slide deck in the chat box. I'm sorry you missed that, but yes, you could. I will go back to my first 2 slides, but if you look in the chat box, that link is the slide deck. So,
Okay. Okay, resolution of singularities. Page 1.
Page 1 is just notes to myself to what I want to.
Okay. All right. Thank you.
Page 2 is just the title, and then page 3, really page 2 of the.
I got it here for this.
Okay.
Yeah, I got here for this.
Yeah. There. That's it.
Thank you.
Okay.
Questions, anybody?
Thank you for your talk, Brent. I use Maple for computer algebra, and I'm not familiar with Sage. Is it open source?
Yes.
Okay.
Yeah. And
Okay, Brent, I have a question. Do you know if Sage can compute decomposition of a radical of an ideal into intersection of prime ideals in polynomial ring, for example, in several variables?
okay, your audio is breaking up. Could you ask again, please?
Yeah, I mean, you have a radical ideal.
Right.
Can you represent it as intersection of prime ideals using algorithm, using program Sage?
Right. So you want to, can it compute the radical of an ideal?
No, you want to compute prime ideals whose intersection is your given radical ideal.
I'm sorry, I'm not understanding your question.
You have to say it
You have
again.
a radical ideal.
Right.
It is intersection of prime ideals.
Right. Yes, I.
Can you compute them?
Can I compute radical ideal? Can I compute like a radical of an ideal?
Can you compute prime ideals whose intersection is given radical ideal?
Yes. Well, okay. Certainly in this context, I mean, in this specific context, I would say the answer is yes. But this is a very specific I mean, these finite dimensional algebras.
Yeah, that's fine. Polynomial ring.
Well, let's see. I don't know off the top of my head just what all Sage implements. Ideals in polynomial. You should be able to do like primary decomposition. I think Singular can probably do that. I don't know off the top of my head, but I would think that primary decomposition in a polynomial
Maybe Singular
ring.
can do this. I'll check. Yeah, thank you.
And let me. I'm just trying to think what I know about that. It might be restricted in terms of the base field. I mean, like it might be able to do it over Q, but it might have trouble if I mean, I kind of recall there's some restrictions in Singular and therefore in Sage as to what exactly your base field is allowed to be.
Okay, thank you.
All right.
Any other questions? Okay, let's thank speaker once again. Thank you.
All right. Thank you all for.
Okay, so who is next?
Our next speaker is Peter.
Peter, okay. So